Essays on the Theory of Numbers by Richard Dedekind. Chapter 1, Continuity and Irrational Numbers. Section 7, Infinitesimal Analysis. Here at the close, we ought to explain the connection between the preceding investigations and certain fundamental theorems of infinitesimal analysis. We say a variable magnitude x which passes through successive definite numerical values approaches a fixed limiting value alpha when in the course of the process x lies finally between two numbers between which alpha itself lies, or what amounts to the same, when the difference x minus alpha taken absolutely becomes finally less than any given value different from 0. One of the most important theorems may be stated in the following manner. If a magnitude x grows continually, but not beyond all limits, it approaches a limiting value. I prove it in the following way. By hypothesis, there exist one, and hence there exist infinitely many numbers, alpha sub 2, such that x remains continually less than alpha sub 2. I designate by alpha 2 the system of all these numbers, alpha sub 2, by alpha 1, the system of all other numbers, alpha sub 1. Each of the latter possess the property that in the course of the process, x becomes finally greater than or equal to alpha sub 1. Hence, every number, alpha sub 1, is less than every number, alpha sub 2. And consequently, there exists a number alpha which is either the greatest in alpha 1 or the least in alpha 2, section 5, 4. The former cannot be the case, since x never ceases to grow. Hence, alpha is the least number in alpha 2. Whatever number alpha sub 1 be taken, we shall have finally alpha sub 1 is less than x is less than alpha, i.e., x approaches the limiting value alpha. This theorem is equivalent to the principle of continuity, i.e., it loses its validity as soon as we assume a single real number not to be contained in the domain R. Or otherwise expressed, if this theorem is correct, then is also theorem 4 in section 5 correct. Another theorem of infinitesimal analysis, likewise equivalent to this, which is still oftener employed, may be stated as follows. If in the variation of the magnitude x we can, for every given positive magnitude delta, assign a corresponding position from and after which x changes by less than delta, then x approaches a limiting value. This converse of the easily demonstrated theorem that every variable magnitude which approaches a limiting value finally changes by less than any given positive magnitude can be derived as well from the preceding theorem as directly from the principle of continuity. We take the latter course. Let delta be any positive magnitude, i.e., delta greater than 0. Then by hypothesis, a time will come after which x will change by less than delta, i.e., if at this time x has a value alpha, then afterwards we shall continually have x is greater than alpha minus delta, and x is less than alpha plus delta. I now, for a moment, lay aside the original hypothesis and make use only of the theorem just demonstrated that all later values of the variable x lie between two assignable finite values. Upon this, I base a double separation of all real numbers. To the system alpha 2, I assign a number alpha sub 2, for instance, alpha plus delta, when in the course of the process, x becomes finally less than equal to alpha sub 2. To the system alpha 1, I assign every number not contained in alpha 2. If alpha sub 1 is such a number, then however far the process may have advanced, it will still happen infinitely many times that x is greater than alpha sub 2. Since every number alpha sub 1 is less than every number alpha sub 2, there exists a perfectly definite number alpha which produces this cut, alpha 1, alpha 2, of the system R, which I will call the upper limit of the variable x, which always remains finite. Likewise, as a result of the behavior of the variable x, a second cut, beta 1, beta 2, of the system R is produced. A number, beta sub 2, for instance, alpha minus delta, is assigned to beta 2. When in the course of the process x becomes finally greater than or equal to beta, every other number, beta sub 2, to be assigned to beta 2 has the property that x is never finally greater than or equal to beta sub 2. Therefore, infinitely many times x becomes less than beta sub 2. The number beta by which this cut is produced I call the lower limiting value of the variable x. The two numbers, alpha and beta, are obviously characterized by the following property. If epsilon is an arbitrarily small positive magnitude, then we have always finally x less than alpha plus epsilon, and x greater than beta minus epsilon, but never finally x less than alpha minus epsilon, and never finally x greater than beta plus epsilon. Now, two cases are possible. If alpha and beta are different from each other, then necessarily alpha is greater than beta, since continually alpha sub 2 is greater than or equal to beta sub 2. The variable x oscillates and, however far the process advances, always undergoes changes whose amount surpasses the value, the quantity alpha minus beta, minus 2 epsilon, where epsilon is an arbitrarily small positive magnitude. The original hypothesis to which I now return contradicts this consequence. There remains only the second case, alpha is equal to beta, and since it has already been shown that, however small be the positive magnitude epsilon, we always have finally x less than alpha plus epsilon and x greater than beta minus epsilon. X approaches the limiting value alpha, which was to be proved. These examples may suffice to bring out the connection between the principle of continuity and infinitesimal analysis. Essays on the Theory of Numbers. This book was written by Richard Dedekind, translated by Wooster Woodruff Bremen, University of Michigan, published by Open Court Press, 1901. It is being read by Jim Renholt, with programming and illustrations by Jim Renholt, 2019. Thank you for listening.